Hi, everybody. My name is Khawaja Shams. I am the CEO and co-founder at Momento. And with me today is
Hi, yeah, I'm Jacob. I'm one of the software engineers working on Valkey and open source. I work for Google Cloud, and I've been working on the Valkey project for about 2 years, and I yeah just recently got added to the set of Valkey committers.
congratulations. I'm pretty excited about Valkey 9 myself. And one of the features in particular, everybody talks about performance. I love talking about performance, but one of my favorite features in Valkey 9 is slot migration, specifically atomic slot migration. What are slots and why are there 16,384 of them?
Yeah, that's a good question. I mean, obviously, I think 16,000 comes from just power of two, it's somewhat arbitrary, but essentially, slots in Valkey, it's a consistent hashing model. When data is coming into the Valkey cluster and a request is coming in, and it needs to be served from one node. The way that the clients pick which node serves what is based off of the key which is then consistently hashed to some value. We take
Mhm.
that consistently hashed value and then we modulo it by that 16,000 to give it a slot. So this way, everyone agrees on what key goes to which node. And then the servers actually do enforce this. So if you go to the wrong node and you say, hey, I want to set this key, and it's not in one of the slots that it owns, it will return back to you a redirection error. So you'll get like a moved response. And then from that moved response, it'll tell you, hey, I don't actually own this, but this other node does.
Got it. So if I have two nodes, then generally speaking, you'll give the first 8192 slots to node A and the remaining to node B.
Yeah, yeah. I think by default, usually people try to do contiguous slot allocations. And it makes things cleaner, and then it's easier to set up that way.
And then if I go from two to four, you'll just kind of split the allocation. Is that generally done evenly with the number of slots, or do you see people in the wild doing their customized distributions?
Yeah, I think I personally have always seen uniform slot allocations. Um, there's definitely some possibilities where you could do interesting things with like, you know, non-uniform slot allocations across nodes. But that would usually be in response to maybe one slot that you know is going to have a lot of hot data or something. But normally, it's a better kind of practice and easier to maintain if you try to keep all the slots uniform sizes.
Who determines how the slots are laid out and which node owns which portion of the key space?
This is how you would bootstrap a cluster. So you might say, here's Valkey CLI, and I'm going to give it three nodes, right? And then those three nodes, Valkey CLI will partition the slots and come back to you and say, hey, does this allocation look good to you? And you say yes, and then it forms the cluster, right? It also comes with the commands for like resharding. So you can
Mhm.
view the topology and decide. Well, actually, I want to move this set of slots to this node independently, and you could do that like regardless of what allocation it had picked after the fact. And then that's where the slot migration comes in, right? There's also a rebalance command, and this just tries to get all the slots to be uniformly allocated. So if you add, like in your example, right, you're going from 2 to 4 nodes. So you could add those two extra empty primaries, and then you would go to the Valkey CLI and you would say, I want to rebalance my slots, and then it would just simply take half of those contiguous ranges and move them to those new nodes.
What was broken with slot migration pre 9.0? Like what was imperfect about it?
Yeah, yeah. And I will say before I mention, in Valkey 9.0, we're not getting rid of the old slot migration, at least just yet. I mean, there's no plans to deprecate that or anything right now. So the way that this one worked was that basically you would go to both the old owning node and the new owning node. We call those like the source and the target node. And you would
Okay.
you would go to both of them and you would say, hey, you're going to start migrating this thing to this other node. And then you would go to the other node and you say, hey, you're going to start importing this thing from this other node. Now, from this state until the very end of that migration, you're basically moving each individual key from one node to the other. And the whole time, Valkey's accepting commands and all this stuff, right? So you have this challenge of supporting serving a slot when it's distributed across two nodes, right? So if you wanted to get a key, and we're like halfway done with this migration process, your client has to first ask the old node, the source node, hey, do you have this key, right? And if that node doesn't have the key, it's going to tell you, well, I don't have it, but maybe this other guy has it. So you have to ask the other node. And then your client would then have permission to go to the other node and prefix your command with asking. So this would tell the other node, hey, I know that you don't own the slot yet, but I have already asked the source node where this key is. And if it did have the key, it would return the value. Otherwise, it would say, no, I also don't have it. And then you would get, that would be a cache miss. Supporting this, distributed slot situation causes a lot of redirections on the client side, and those end up showing up in your P90 and P99 latencies. And then finally, this one becomes a real big problem if you have these collections of lists and hash and stuff like this. If you have one that's really big, it may get big enough that moving that as a key atomically, so basically you have to move it from one node to the other node. And doing that can be very difficult because the actual serialized size of that value can be gigabytes, right? And you then have to block the main thread, serialize this big key, then try to send it over to the other node while you're blocked, right? And then the other node has to then process the big key and then return back to you, yeah, I processed it. And you're starting to run into, at this point, some of the limits of what Valkey can support regarding a single request. Like every string in your request can only go up to 500 megabytes by default.
Hmm. Hmm.
That's to prevent, someone connecting and then saying, hey, I have this big key for you, and then just dumping, gigabytes and ooming your server. So there's this limitation, and you have to, make a difficult decision if you come across one of these large keys and it's not able to be imported. You either have to increase that limit temporarily to get that key through, or you have to shrink the key some way, delete the key, finish the migration, and then repopulate the key. And even if you adjust those limits on what we can accept, it still takes a very long time. And in this whole time, you have to kind of block the main thread on both servers. So I guess the last thing is just that it's very slow the old way, because you needed to move each key kind of individually. And there was configurations for batching that, but you ended
Hmm.
up kind of absorbing all these round trip times into the overall time of the slot migration itself.
When you're migrating in the previous style, are you migrating one slot at a time, or are you migrating one key at a time? Like how does the process actually work to identify what needs to be moved from the source to a target?
Once you've established the migrating and importing states, you first just go to the old node and you say, hey, give me 10 random keys in the slot. And then now for each of those keys, you're now calling this other command called migrate. And migrate basically, serializes the key that you give it into a memory buffer, ships the memory buffer over to the other node, waits for the other node to come back and say, yep, I got it, and then deletes the key locally and then returns back to you, yep, I did it. So you're doing that basically in a while loop while the get keys in slot is greater than 0. Ship some keys over, and you do that until it says, yeah, I have nothing left. And then at the very end, you can go to both nodes and you say, hey, you both are done. This new node owns the slot now.
That may actually prolong your actual migration. And during that time, you're kind of at risk because there's all these redirections happening between
Mhm.
the client and so forth.
Yeah, you have to make these trade-offs between, like, do I want to have more things in flight at the same time and potentially more of my data being redirected, or do I want to go single slot at a time? So that's where I said it takes like a minute to do a 3 to 4 shard migration, because you got 4,000 slots you're moving. And
Hmm.
for each one of them, it's like 2 round trips at the beginning to set up the importing and migrating state. And then like 3 round trips per each batch of keys. And then
Hmm.
2 round trips at the end. So even with not that much data, like you're spending so much time just iterating and sending off these round trips.
For each slot, right?
Each slot, yeah.
Okay.
And then actually, I think people underestimate this, but each slot also becomes one topology change. And then every time a topology change is detected on the client, it kicks off a lot of
Hmm.
processes to refresh the topology.
Yep.
So if you're moving 4,000 things, you end up actually doing 4,000 different topology changes. Like this slot moves from here to here, this slot moves from here to here, doing that over and over again. Each one of those takes CPU on your clients. Every single one of those ends up impacting your QPS.
Got it. Now let's switch over to the atomic slot migration. How does that work?
So the way that atomic slot migration works is very similar to how we replicate to our replica nodes from a primary. And so that kind of goes through three phases. The first phase is this kind of like snapshotting. So the way that replication works, and we use the same idea here in slot migration, is we fork a child process from our parent process using like the Linux fork. And so
Hmm.
behind the scenes, Linux does a lot of accounting to make sure that that child process's memory doesn't change from that point onward, as the parent process can still serve stuff. So parent process is still alive and serving. The child process then has a point in time snapshot, and we use that to iterate over the whole key space and send it over to the new node. So the new node is kind of storing these keys in a staging space, right? There's no confusion here about what's staging and what isn't because it's divided at the slot level.
Hmm.
So we ship over the contents, and they're inaccessible to users at this point because, as I mentioned, the slots aren't actually owned on the other sides. So we're replicating this snapshot, and that's the phase one. Phase two is during that snapshot, we're capturing all the work that's happened on the parent process while we're shipping off that snapshot. Basically, anytime there's a change, we check what slot that a change is targeting, and if it's in the migration, we just keep a buffer of those, and we
Hmm.
can accumulate those on the source side. Once we notice that the child process has finished snapshotting everything, the parent process then starts to flush that buffer over to the target node. And we call this kind of like the incremental changes, the streaming phase. So we're streaming
Hmm.
these incremental changes over. And then lastly, once we've flushed out the buffer completely to the TCP stack, we then pause new writes. And this is our finalization phase. We put a marker in our stream to the target node. And then the target can tell, hey, this is the point in time when I know that the source node is completely paused and there's no new data. And then the target can cleanly take over. So at the high level, it's very automatic. You know, you kick off a migration. It does this three-phase process in the background, and then your clients, your operator or user can pull that migration status like a long-running operation.
Is this happening one slot at a time still, or is it happening for all the slots that need to be migrated between a target and a source?
Any number of slot ranges can be put into one migration.
Nice.
So you can migrate as much as you want in a single migration. If you like doing it single slot at a time, you can still do that, right? And there could be some benefit there, right? Moving less data at a time
Hmm.
might make it less impactful on your server, right? But by default, is it's going to batch everything as much as it can, and this gives you a lot of benefits, especially in the latency part, right? Since now you don't even need a round trip per each slot, right? You just do one operation and it does a full dump of everything. And then, especially on the client side, it's much less impactful because one topology change, and the topology change happens at the very end after all the data has already been transferred. And there's
Hmm.
no asking redirections or anything like this because we're copying all the data over before we finish the slot migration, right? You could kind of see how this fixes some of the problems that we had before, so that your clients don't have to be aware of the slot migration. It's just one atomic handover, and that's where the name comes from, atomic slot migration.
That's awesome. Jacob, I am really excited about what this means for availability, resilience, and just performance of Valkey. It is one of the many things that are in Valkey 9. Thank you for your contributions to the Valkey project and for championing atomic slot migrations and getting them delivered in 9.0. Congratulations.
Thanks, Kwaja.